Any other questions right now? Anyone about to come up with a question? All right, let's get this done. All right. So there's a mistake on the board. What's the mistake? There are.
Voltages in the vector.
Yeah, I just realized there were a couple other mistakes there too. All right, so besides the labels being wrong, let's see, so this is 2 charges. This is 1 charge. This is the vector. All right, so. There's a mistake up there. I know we talked about it last time. Although the chart I put up at the end of class.
Joules per
Oh, the
coulomb.
constant.
Yeah. And,
Joules per coulomb. Units per voltage. Scalar.
oh, well, that's blank right now.
Oh.
But, yes, to what Precious said, plus some constant.
Oh.
All right, so the missing piece here, obviously scalar 1 charge. We talked about it in the lab on Thursday, last Thursday. Hinted at it last week. But the same way that we go from force to electric field by getting rid of one of the charges, by getting rid of the recipient, I guess, of the force. Do the same thing here. We do have 2 charges here. If I get rid of just one of the charges, get KQ over R. And this, the symbol for it is a capital V, and this stands for electric potential. Plus some constant. Whereas up here, this U is electric potential energy. And we've gotten away with just saying, hey, what's the potential, referring to the potential energy, but we can't do that anymore. If I say what is the potential, presumably we're talking about electric potential, although there's gravitational potential, there's other potentials. Within context, I should be able to get away with just calling this potential, but I still need to use the word potential energy. Energy has to be used if I'm referring to this up here. And we don't use potential energy a whole lot in this. We stick mainly with electric potential after this point. However, this doesn't go away, just don't use it anywhere near as often as we will this. The units, as Zachary was talking about, when we divided out a charge here, we basically are divided by coulombs, and so the SI units of electric potential is the joule per coulomb, which is too much for physicists to write, and so that is the volt. named after Volta. I would say it's probably in the minority of units which are not explicitly named after, using the name of the person. Farad also named after Faraday. Now, I have not talked about the voltage yet. So let's talk about voltage. I notice also, before we do that, since I have a V there and a capital V here, these V's do not mean the same thing. And as I probably mentioned before, in math class, V would be equal to 0. In physics, this means that the electric potential is equal to 3 volts. These V's are not the same, unfortunately. They ran out of letters. So if I have a spot here that is 3 volts, a spot here that is 4 volts, and a spot here that is 5 volts, and I have a charge that starts at the 4 volt and goes to the 3 volt. What is the change in the electric potential?
1 volt. 1 volt.
No.
1
Negative
volt.
1.
Change is always final minus additional. Since I go from 4 to 3,
Negative.
it's
Okay.
negative 1 volt. So this is the electric potential difference. More commonly called voltage. And it's probably mentioned on Thursday, some textbooks go overboard to distinguish between electric potential and voltage, or electric potential and electric potential difference, and some textbooks just play fast and loose. I will try to emphasize when it's electric potential and when it's electric potential difference. If I start from 4 volts, I take the following path. What's the voltage there?
2 volts. Oh,
1 volt.
1 volt.
Yeah, Zachary, you're just ahead of your time. Because it doesn't really matter the path that you take that goes in between. I mean, ultimately it goes back to the fact that electric force is conservative. So it's path independent, just cares about where you started, where you ended. All right, so we've now filled that in. Let's talk about why charges will attract or repel in terms of potential energy, and then we'll do it in terms of electric potential, and we will have completed our why does one thing happen, or why does attraction and repulsion occur, and we'll have 4 different explanations for the exact same thing. Let's see, we've got room over here. So let's say I have a positive charge here, and I have a positive charge here. So we'll just assume that this one is fixed. This is going to move, and the initial speed is 0 meters per second. So basically I've got a positive charge here, and I just stick another one, just pop it right there. We'll call this cleverly Q1 and Q2. We are dealing with the electric force, which is conservative, therefore energy is conserved. Therefore, since energy is conserved, what's going to happen when I put this charge down in terms of energy? Let's be more specific. In terms of the kinetic energy, what's going to happen when I put this down?
It's going to neutralize. It's going to want to reach a position where there's no built-up potential.
It's going to build up potential.
No, it's going to want to reach a place in which there's no build-up potential energy.
Sorry, I think I missed a few keywords there. Let me get closer.
will move to a position in which there is less potential built-up energy.
Oh, it'll move to a place with less potential energy. Therefore, what happens to the kinetic?
Increases.
Okay, so kinetic energy goes up. Since energy is conserved. And also recognize this E is energy as opposed to this E over here, which is the electric field magnitude. All right, go ahead. Put the absolute value sign around over there. Potential energy goes down. Well, I got my formula over there that my potential energy is equal to K Q1 Q2, I'm doing capital Q's now, Q1 Q2 over R squared. If my potential energy is going to drop, what has to happen?
The distance has to increase. The distance has to increase.
And as the denominator gets bigger, my potential energy gets smaller. So from an energy point of view, my kinetic energy will increase, which means my potential energy must decrease. And as the fraction, my potential energy will decrease if my denominator gets bigger. In other words, R increases. If we tacked on the constant, it doesn't change any of the analysis we just did. So, like charges repel. And unlike most of you, Austin now has an alibi for this time period. It's on camera. If you'd like me to edit that out later, then I can. All right, so now, how about attracting? Negative, so this is fixed in space. And I put a negative charge here. Is kinetic energy of the negative charge going to increase?
Yes.
Is energy conserved?
Yes.
So potential energy must get smaller.
No. Oh, yes.
I hope so. If, otherwise, we've got some mass energy that's going to get larger in mass or smaller.
Fusion reactions.
However, my potential energy formula doesn't change. But with fraction, I got a fraction here. Don't fractions get big, get smaller if the denominator gets bigger?
Yes, but we are acting as if the zero is the equilibrium of a spring. So the for a spring constant, or its unstretched length,
Right.
is where zero would be in this analogy of potential. Built-up potential is simply the withheld forces at work.
Wow, that is convoluted. I don't think that gets us any closer.
Well, if we're negative, right, one of our charges is negative, so we have a negative value. We're wanting to move from the negative side to zero. If we're positive, we're wanting to move.
We're wanting to move from the negative side of what?
Number line, value, magnitude. When you have a negative potential, it's still potential.
Yeah.
So as we move back to zero, we are releasing that potential energy.
Oh, if you're gonna use that analogy, then, because I don't have a constant out here, I'm making the claim that the potential energy equals zero when R is infinitely large. So my potential energy drops off to zero when I'm out of sight.
I would not agree with that.
So there should be a constant added on here?
There is a bell curve that occurs, or a parabola that occurs for electrical forces.
It's a 1 over R squared,
Before you
it's not
get-
an R squared.
But before you get to infinity, you still have magnitude. So as it approaches
Yeah.
infinity, it's zero, but if it is at the point exactly, it's still zero.
At the point.
Of this, or a spring, in relation to like a spring constant, where it's unstretched length in relation to whether it's negative to positive.
Yeah, the breakdown from the math point of view is that the potential energy for a spring is related to, well, it is defined at 0 to be basically where equilibrium is,
Right, so if you stretch.
every time I've dealt with it. It is potential energy, so you could always tack on the constant and rechange that.
Right,
But I think the spring analogy is the wrong way to go, because this is an inverse relationship and the other one's a
well, it's just like if you were.
reverse relationship,
Well, it was like if you were stretching a spring versus compressing a spring.
right?
The unstretched length remains the same, and that's where I put my zero. And so if I have a negative magnitude because of the positive and the negative product above the denominator, as I move closer to zero, I am releasing potential energy.
And 0 is an infinite distance away. You seem to be putting 0 at some finite spot.
Yes,
So you're,
zero to me would be the unstretched length of a spring. The displacement,
yeah, but what's unstretched here?
in my mind, it's zero distance, but
Oh, when it's on top of it?
no, well, yeah, for negative, and then I just flip it for positive as far as the infinity. It goes from 0 to infinity, when it's too positive.
Ultimately, we care about the change in potential energy. So no matter where we put 0,
Right.
it doesn't, that's not going to,
Picture if I have a positive and a negative charge. That is
Okay.
one material of spring. The unstretched length is a specific place. For me, it's 0 because I know that a positive and a negative attract. At 0, the potential energy will reach a negligible amount. If it's a positive and a positive, that's a different material. Its unstretched length is at infinity. And therefore, the farther away we get, the more released potential energy. I treat them as two different sets.
yeah, I think we're trying to come up with a rule that works regardless of what the charge is.
Yeah, which this doesn't.
Yeah, I can't help but think that your spring analogy just is the wrong path to be going down. I'm trying to force it to work, but I feel like I'm jumping through hoops to make that work.
Yes.
So I'm going to abandon your spring analogy.
It works up here.
Okay? I hope it continues to work up there. All right, so back to my question of, I know from dealing with electric field and dealing with forces, I know that they will get closer to each other, which means R is getting smaller. But doesn't that mean the fraction is getting bigger? But my potential energy is supposed to be getting smaller. How can my potential energy drop if my denominator is getting smaller?
I don't know why, but I would think like the closer the two oppositely charged particles get to each other, the less likely they are to separate.
True. From a force point of view, that force becomes a lot stronger in this case.
So if forces being charged holding them together, less likely to separate them. Thus the potential energy decreases.
So if the force is stronger, less likely to separate, so the potential energy, so the potential energy gets smaller? I think that's what you said.
Yeah, but I don't know what I'm saying is right.
Okay. I'm not 100% sure either. I'll agree that they will get closer. I think if otherwise, what we've been doing for the past several weeks, completely wrong. However, from a math point of view, if they get smaller, that means R gets smaller. From a physics point of view, I know potential energy is supposed to get smaller. So how is it that R gets smaller and my potential energy gets smaller at the same time?
It has to go back to the work equations.
Let's do it from a math point of view. We don't need to do physics at this point.
Okay.
This is a math question. I have an equation for potential energy. Pretty sure all of you have dealt with fractions before.
Yeah, the magnitude of the charges would increase, like,
No, charges are fixed. We're not gonna change the charges. You know, assume everything in the numerator is constant for a problem.
Is it a unit issue? Is it
Nope, not a unit issue. I'm guessing you probably have seen examples of this for 10 years, just with numbers instead of letters.
Maybe the inverse of R,
Pardon?
maybe the inverse of R, or am I thinking wrong?
It's the multiplicative inverse. That doesn't change anything that I've said here. When, ultimately it comes down to, when does a smaller denominator mean a smaller number?
Is the one that's
Negative.
Yes, which is what we're dealing with here. They're opposite charges. I don't care which one's Q1, Q2, I know they're opposite charges, so this is a negative fraction. So as R gets smaller, we get a smaller potential. -2 is greater than -10. But the magnitude, the absolute value gets bigger, but the fraction itself gets smaller. So it holds either way. If they're the same charge, this is positive, a positive fraction, so as R gets bigger, my fraction gets smaller. But if they're opposite charges, this is a negative fraction, and as R gets smaller, the potential energy gets smaller. Did I misspeak that?
No, it's perfect, it's just, I way overthought it.
So we have a third explanation for why charges attract or repel. Now let's come down to potential. Just start out with positive charges here, so I've got, let's just do a real example, 5 nanocoulomb charge. Let's actually make 12 nanocoulomb charge. If I am 1 meter away, like an electric field, we don't find the electric field with 2 charges, we find the electric field of 1 charge at some point in space. We're finding the electric potential at some point in space here. So if that's 1 meter away, what is the potential at this point? Assuming V equals 0 as R goes to infinity.
$108 volts. Yeah, 108 volts.
Okay. Wait, I'm 2 meters away? Oh, sorry, an additional meter, so I'm 2 meters away from my 12 nanocoulomb charge?
54.
Go 1 more meter.
36.
And so on. If this is a negative 12 nanocoulomb charge, then this would be 108 volts, negative 108 volts, negative 54 volts, negative 36 volts.
In terms of the electron, a negative voltage means that the electron would be repelled through the circuit rather than pulled?
Well, let's come up with a general rule.
Okay.
So I'll start out with a positive charge. I put a positive charge here, and we know from the other 3 things that we've done, which way this positive charge is gonna be forced. Which way will it go?
Voltage is going away.
Away, all right.
Okay.
In terms of potential, which way does it move?
Down.
Lower potential.
Okay. So I know that positive charges, this is the generalization, positive charges want to move to lower potential. If I put a negative charge there, which way is the negative charge gonna go?
Towards the highest potential.
So negative charge wants to move to higher potential. And we can see that down here also, that rule still applies if I put, so I got my 12 nanocoulomb charge there, if I put a positive charge here, it is going to move towards it. So it is going to move to a lower potential. If I put an electron here, it's going to go this way, it's going to move to a higher potential.
Okay.
Is that always? No matter the sign of the charge or?
Yeah, so if I didn't tell you the source of it, I just told you I had, actually, the example I did before. I had a 3 volts here, and I had a 4 volt here, and I had a charge that went from there to there. If I just put a charge there and let go and it moved that way,
It has to be positively charged.
yep, that would have to be positively charged. Now, I can force charges to go against it by shooting them in the other direction. I can take a positive charge and shoot it that way, but it's gonna slow down, and give it enough time, it'll stop and then be pulled back. So this is half of it. The other half of it is that potential decreases, and let's go for some stunning color. There's no purple over here, so let's do that one. Potential decreases as, let's see, decreases farther from positive charge and closer to negative charge. Based upon the formula. And I do want to emphasize these formulas that I have over here. Point charge formulas. Formulae. Let's be sophisticated.
So when they approximate the voltage of a system, when they approximate the voltage of a system, are they placing that test as equidistant from the positive and negative as possible, or are they running a simulation?
When you talk about a voltage of a system, you're talking about the difference between 2 points. So if my system just consisted of these 2 points here, my voltage is either plus 1 volt or minus 1 volt.
Right.
So they're not establishing where 0 is at all, they're just saying, well, I don't care where 0 is, I know there's a difference of 1 or negative 1, depending on which way you go.
Okay. So voltage is just potential energy, the energy difference.
Yes.
Okay.
No. It's the potential difference, not energy difference.
Okay. Is there an equivalent for the electric potential energy for voltage?
I mean, they're definitely related to each other.
Right, but there's not like a phrase that we use colloquially.
Oh, like, electric potential energy difference?
Yes.
It would just be the change in potential energy.
Okay.
That's all I've seen. Now, it's possible you get into specializations and somebody's come up with one, but
Okay.
physics doesn't take it that far, at least not that I've seen. Although I did once see an article of somebody who talked about how the order in which letters should be written when you're writing an equation. And so it's possible somebody has decided to do something like that.
Wouldn't doubt it.
All right, questions to hear? So let's do some problems.
Dr. Boswell. I don't wanna interrupt, but later on, I have some questions about the lab.
Oh. We're only on time. We've got basically 50 minutes or so. You know what? Since this is a transition here, why don't I go ahead and take questions about the lab first, and then we'll do some point charge formulas and distribution formulas.
So I'm confused on how to, like, draw the tangent line.
Okay, so you've got your positive and negative charges here. I assume for part A as opposed to part B. All right, and they're gonna go roughly like this. Now, because that's closer to an ideal, yours might be a little bit kinked, depending upon your equipotential line. Hopefully not that bad. Like if some of you got something like that.
It might be.
Or is, what if they overlap? What do you
Yeah.
The electric field lines overlap, or your equipotential lines overlap?
Yeah.
Yeah.
Yeah, Nobel Prize? They should not overlap.
Unless there is a heavy magnet over there.
Yeah, they still shouldn't overlap, which means that,
No, I'm just saying they would get interference that would suggest, like, they would graphically represent it, but it wouldn't actually be overlapping. It would
yeah,
just
I
be-
mean,